All right, so whoopsie, that's fun. Ignore that. Okay, so today we've got section 4, which is measures of relative standing in box plots. So the first thing we talked about is the z-score. So a z-score is a standardized value that measures how many standard deviations a number is away from the mean, above or below. Positive values will be above, negative numbers will be below. So depending on whether you have a sample or population, you have these two different formulas you can see. So for a sample, it's z equals x minus x bar over s. So x is the measurement value itself, x bar is the average of the sample, the mean of the sample, and s is the standard deviation of the sample. For a population, it's in general the same thing. X is still the measurement, except since you have a whole population, the mean now becomes mu, and the standard deviation becomes sigma instead of s. Because remember, Greek letters are for populations. English letters are for our samples. So really example 1 says, it's referencing the previous section, use the coefficient of variation to compare variation among chocolate chip cookies versus variations among weights in Coke cans. So we're going to look at the individual data values for this question. So which of the following two data values is more extreme? Chips Ahoy with 30 chocolate chips gives you the mean for 40 is 24 and the standard deviation is 2.6. Or the can of Coke that has a weight of 0.8295 pounds, tells you how many cans of Coke you have versus their mean weights here and their standard deviation there. So says both of the above data values are the largest values in their sets, but which one is the most extreme? So which one is more unusual than the other one? So we need to calculate. Oops, I'm off the screen. We need to calculate the z-scores for both of these values. So for the cookie, our z-score is going to be our measurement, has 30 chocolate chip cookies, so that's x, then minus the average, which up here, the average is 24, and then we divide by the standard deviation, which is 2.6. So that's going to give us a z-score. Let me grab my calculator. 30 minus 2.4, or 24, divided by 2.6. So this comes out to be a z-score of 2.31. Typically we round z-scores to 2 decimal places. So for the Coke, similar setup, its average, or the can we're looking at is 0.8295. The average is 0.81682. And this is all over the standard deviation, 0.00751. So 0.08295, oops, put that in the wrong place, 0.8295 minus 0.81682, and then divide all of that by 0.00751, and we get a z-score of 1.69. So since this z-score is larger, this is the more extreme value. It is 2.3 standard deviations away, whereas this one's only 1.7 standard deviations away. So this one's farther from the center, the average value, than this one is. So we talked about the range rule of thumb being, this was mentioned before, so z-scores of less than -2 or more than +2 are unusual. So this would be an unusual cookie, this would not be an unusual can of Coke. So example 2 down here says it's a pulse rate of 48 beats per minute, unusual if the mean is blah, blah, blah. So we need to find out what the z-score is for 48, because if it's more than +2 or less than -2, it is unusual. Otherwise, it's not. So we've got z equals our measurement, which is 48, minus our average, 67.3, all over the standard deviation, 10.3. So if you notice, this one's going to be a negative z-score, because our measurement is less than our average, and that's fine. Z-scores can be negative. And we divide by 10.3, and this comes out to be negative 1.87. So this is not unusual, because it's not less than -2 or more than +2. But since it's negative, there's no way to be more than +2. Alrighty, so that brings us to our properties of the z-score. So once again, just the measure of the number of standard deviations. No units of measurement. If you think about the math, the units would cancel. When it's unusual, if it's less than, you get a negative number. So that's where you get your case where you have negative z-scores. So the next thing we've got is percentiles. So measure of location, P1, P2, P99. You're probably most familiar with percentiles from like standardized tests. Sometimes they'll report you're in the 75th percentile, you're in the 80th percentile, you're in the 99th percentile. That just tells you what percent of the values fall below your score. So the 50th percentile, 50% fall below your score. Up here, P2, the second percentile, 2% of values would be below your score, so on and so forth. Okay, so example 3 here. Oops, sorry. There's your formula for percentile value. The number of the values less than the given. So if you're looking for of any given value x, you count the number of values less than that, and then you divide by the total number of values and multiply by 100. So for example 3, so this is the chocolate chip cookie data again, but they're now ordered to make it a little bit easier to see. So normally when you do a percentile, you need their values ordered, means you need to find the number that are less than a given value. Find the percentile of a cookie with 23 chocolate chips. So our x value is 23, that's the measurement we're looking at. So if I look at my formula, which is still hopefully on the screen, it's the number of values less than x. So I need the number of values less than 23. So that is just this top row. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're gonna have 10 on top. On the bottom, the total number of values. So there's 10 values in a row, there's 4 rows. So there are 40 values, and then times 100 to make it a percent. So the percentile for this, 10 divided by, that's 1/4, so 0.25 times 100. So this is the 25th percentile. So this would be P25, the 25th percentile. All right, so example 4, so use the same table, but now we're working backwards. We want the 18th. We want to know what number gives me the 18th percentile. So to do that, we're working backwards. So 18 is equal to what number over 40 times 100. Notice that 18 is the percentile, so it stays 18. So I need to divide by the 100. So this becomes 0.18 equals x over 40. And then multiply both sides by 40, sorry, I'm at the bottom of the page, x will equal 7.2. Now, the thing is, you have to be careful because that's not the number of chips. That's the number of values less than the chips. So the thing is, since this number is more than 7, I have to round it up. You always round up, doesn't matter if it's just a little bit. So this would actually become 8. So 8 numbers are less than my measurement. So I go back up to my table, 1, 2, 3, 4, 5, 6, 7, 8. So 22, the actual value would be 22 chips. You have to be careful, this isn't, if you look at your formula, this is the number of values less than x. It's not what is the value of x. So in this case, I probably should have used a different variable. I should have used like n or something like that to make it more clear. Okay, example 5. Whoops, we're gonna need that same table, so we can't have it on screen as well, but you can see it too. All right, find the 25th percentile. We actually already did this problem because we worked it forwards the first time. It's 23. But anyway, we'll work it the long way. So the 25th percentile is, we'll use n this time, times 100. So divide the 100 across, 0.25 equals n over 40. So n is equal to 10. So there are 10 numbers less than my number. So if I go back to my table, I count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my 10 numbers are less than this, whoops, off the bottom of the screen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers are less than this one. So since n is 10, you're looking for the 23rd or the 11th number. So x is 23. And this is essentially example 3 worked in reverse. Okay, so there are some percentiles that are important, so they get their own names. They're called quartiles. Q1, 2, and 3, they break it up into quarters. So Q1 is the same thing as the 25th percentile, because it's the first quarter. The second quarter would be the 50th percentile, and the third quarter would be the 75th percentile. So you're counting the number of quarters, or 0.25s. So find the value of the first quartile, Q1. Now I'm not working this one again. It's the same problem as this one. The first quartile is the same thing as the 25th percentile. So X is 23. Again, same thing. The math would be exactly identical to this problem. You'd convert the quartile into a percentile and then run the formula. So first quartile is 25%, so 25. And then all of this math is the same. So same thing again. Just some definitions down here. You sometimes see what's called the interquartile range, which is the difference between Q3 and Q1. The semi-interquartile range, semi means half, so you just take your interquartile range and divide by 2. The mid-quartile is the midpoint of Q1 and Q3, so you add them up and divide by 2. It's the average. And then the 1090 percentile ranking is the difference between the 90th and the 10th percentiles. Okay, so we also have what's referred to as the 5-number summary and the box plot. So the 5-number summary of a group of numbers includes these 5 values. Now these are listed from least to greatest, so minimum, the first quartile, the second quartile, which is actually the same as the median, the third quartile, and the maximum. And a box plot organizes these into a visual representation. So use the chocolate chip counts listed in table 3 to find the 5-number summary. Now, I will do this longhand. There is a way for your calculator to do it, but we'll talk about that at a later date. So here we go. If you look at these numbers, so I need to find, let's see, so I need to find the minimum, I need to find Q1, I need to find the median, which is the same thing as Q2, I need to find Q3, and I need to find the max. So these are the values I'm looking for. So min and max are the easiest ones to find. They're the least and the greatest. So minimum is 19, maximum is 30. 19 and 30. Now, the median is the next one you find. It's the number in the middle. So I have 40 numbers. So the middle number is between the 20th and the 21st. So since there's an even number of numbers, when you find the median, you take the middle 2, 24, in this case 24, and average them. So 24 plus 24 is 48. And you divide by 2. So the median is 24. Now it's going to be 24 because the numbers you averaged were the same. Now Q1 and Q3, you can kind of do something similar. So the median actually sits right here. It breaks your group into 2 half groups. So there were 40 numbers total. The bottom half has 20 numbers, the top half has 20 numbers. Q1 is then the median of just the lowest 20. So it's going to be the average of this number and that number, the middle 2 numbers, and since I still have an even number of numbers. So Q1 is 22 plus 23 divided by 2, which is 22.5. And I can repeat that process for Q3. That's the median of the upper half. So that's the average of this number and that number. Now, since they're both the same, I'm going to skip the math because the number halfway between 26 and 26 is 26. So there's your 26. Okay, so there's my 5-number summary. All right, so box plot. So we're going to use these numbers to construct a box plot. So to do a box plot, you start with essentially a number line. So I'm going to start down here at 19, and we'll count by 2's 21. I started at 19. Whoops, there you go. 19 because that's my smallest number, and we'll count by 2's because that should probably get us high enough. Oops, that'd be 31. And that'd be as far as I need to go because my biggest number is 30. So there's the minimum. My scale includes, so find the 5-number summary, which we just did. Construct a scale, which is what here. That includes the minimum maximum data value. So I have my smallest number has to at least be less or equal to than the minimum. The biggest number has to be equal to or more than the maximum, which they are. So it says construct a box or a rectangle extending from Q1 to Q3 and draw a line in the box at the value of the median. So what that looks like is, so Q1 is 22.5, so that's about here. Whoops, yeah, it's 22 is about there. So this is a real rough sketch. 22.5, there's Q1. Q3 is at 26, which is halfway between 25 and 27, and then we construct a rectangle. So these two vertical sides are Q1 and Q3. And then we draw another vertical line in the box at the value of the median. The median is 24, so that's right here. So that's my median. Now, so that's the box plot. Sometimes these are also called box and whisker plots, so now comes the whisker parts. Draw lines extending outward to the minimum and the maximum values. So the line comes out going this way to the minimum, which is at 19, and goes up this way to the maximum, which is at 30. So that's the box and whisker, or the box plot for those numbers. Okay. Let's see, use table 1 to construct the 5 corresponding box plots, and then compare the results. I'm not going to worry about this one. If you really want to see it, shoot me an email and I'll record a separate video. But table 1 has 5 different measurements, so I don't want to use a whole bunch of time on this video to do that. If none of you email me, we'll let it slide. Okay, so the last thing here is you got outliers and modified box plots. So an outlier is any number that's more than Q3 by 1.5 times interquartile range. So we'll have to figure out that value first, which is Q3 minus Q1. And then multiply by 1.5, and then add it to Q3, and that'll tell you the cutoff for the outliers. So modified box plot, you mark your outliers with either asterisks or stars or something like that, and you don't extend the whisker out to them. So that's this part here. So let me find the table. I will work this one. So the Hannaford chocolate chip numbers are, we'll jot them down real fast here. I don't want to, 15, 13, 15. Oh, these aren't in order. Okay, so I'm going to show you how to do this, at least on my Casio calculator. So hopefully you can see that at least a little bit. TIs have something very similar. If you're curious, it shouldn't be too bad. All right, so I just need to enter all my numbers. These are just the values from table 1, 15, 13, 16, 11, 14, 12, 13, 12, 14, 12, 16, 17. Oh, shoot. That should be 16, 12, 16, 17, 14, 16, 14, and 15. 24 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And make sure I didn't typo any of those. Okay. So calculate one variable. And if you look, my calculator will give me, oh, right there, the 5-number summary. Minimum, Q1, medium, Q3, max. So let's jot these down real fast. So the minimum, 11. Q1 was 13. The median is 14. Q3 is 15.5, and the max is 21. So the interquartile range is Q3 minus Q1. So 15.5 minus 13, so that is 2.5. Then I need to multiply that by 1.5. Let's see here, 2.5 times 1.5. So that is 3.75. Okay, so in this case, if you look here, my maximum is more than 3.75 above my Q3 value, which means I do not include that guy as my maximum. I work backwards to the next previous value in my list, which if you go back and look at the list would be 17. And 17 is less than 3.75 away from the maximum. So an outlier in this case is anything less than 11 minus 3.75. These are the outliers. or anything more than 15.5 plus 3.75. So 15.5 plus 3.75, this is 19.25. So I have to throw out that maximum. That would get a special symbol, and I would go back to my list and find the next number that is less than 21, which is actually 17. So this value is 11 minus 3.75. So, oh, sorry, not 11, it would be 13 is the Q1 value. 13 minus 3.75, which is 9.25. So this minimum isn't an outlier because it is not less than 9.25. So when I do my box plot, so there's 11, 13, 15, 17, 19, and I'm going to put 21 because I'm going to mark it with a special symbol. So the minimum is at, sorry, we do Q1 and Q3 first. So Q1 is at 13, 15.5, we'll call it about there. Draw my box, put the median in, 14. Whisker down to the minimum, so that look like that. Now 21 isn't my maximum, so I'm just going to put an asterisk there. And then if I go back to my list, 17 is the next biggest number if I throw out 21. So my graph is actually going to look like that. So 17 becomes the new maximum because I had to throw out my old maximum. And you keep throwing out maximums until you get one that's less than 19.25. Because that's the biggest value you're allowed this before it doesn't count as an outlier. All right, so that wraps up, I believe, the last section.